Welcome back. We are going to learn how to use Zaytsev's rule to predict the major and minor products in an E2 reaction. And I am going to show you cases in which Zaytsev's rule does not work and help you identify when that is going to happen and when that anti-Zaytsev's product is actually going to be the major product. This example shows Zaytsev's rule working. So we have 2-bromobutane. The leaving group is this bromine. You've already identified that from a carbon-bromine bond in the previous example. And a way that these overall reactions are often written is with the base and the solvent above and below the reaction arrow. So this is going to have more than one product. If you want a chance to try to predict what it is yourself, go ahead and pause to figure that out. But I'm going to jump right into writing them. We can have 2-butene or 1-butene. And these are not going to be in equal amounts. They are not going to be in amounts that you might guess just statistically between 2 hydrogens and 3. No, we need to learn Zaytsev's rule. Zaytsev's rule says that the more stable alkene is going to be the major product. And the way that that is defined in Zaytsev's rule is that the more substituted alkene is more stable. So what you need to do is find the 2 carbons involved in our new double bond and count how many other carbons are directly bonded to them. Now, I think that this is a lot easier to see in line structures, so let me just redraw these. Down here, we have 4 carbons and a double bond between carbons 2 and 3. But not counting each other, how many other carbons are bonded to these 2? 1, 2. So this is a di-substituted alkene. Over here, we're doing the same thing, but this is carbon number 1, so this is only hydrogens over here. The total number of other carbons that these 2 are attached to is only 1. This is less substituted alkene. This is less stable. So Zaytsev's rule says that this more stable alkene is our major product. This major product could be in either cis or trans configuration. You might be used to calling it E or Z configuration. And we will later figure out which is the major product between cis and trans. But I've got to teach you more first. We need to build up to that. Here's a little pro tip about Zaytsev's rule. Zaytsev's rule talks about the products and their stabilities, but in that moment when what you have in front of you is the reactant, what I do is count the number of hydrogens on each of those beta carbons. And yes, you need at least 1, but once you get there, the beta carbon with the fewest hydrogens ends up being the one that reacts to make the major product. That's just an easier way to see it up front. Now, as scientists, we do the best we can with the information that we have. And that is exactly what Zaytzev was doing. But we know more now. And there are a number of cases where Zaytsev's rule doesn't work and that anti-Zaytsev's product predominates. Let's talk about those. So first, Zaytsev's rule does not work when conjugated double bonds mess it up. So first, let's figure out what Zaytsev's rule would say. This was our leaving group, and we could choose between reacting with these hydrogens to make a double bond here for this product, or this hydrogen to make a double bond here for this product. Zaytsev's rule says to count how many other carbons are on this new double bond. 1, 2. 2 carbons directly bonded to it. But over here we have 3. 1, 2, 3. So Zaytsev's rule says that this would be our major product because it is more substituted. But no, that is not true here. This is our major product in this case. And the reason for that is that we have a conjugated double bond system. Whenever you have the pattern of double, single, that pattern over and over again, that's called conjugated double bonds, and it's extremely stable. And that extra stability is going to be our major product, whereas this is not conjugated. We have double, single, single, double. That ends up being our minor product. So Zaytsev's rule failed here. Second, Zaytsev's rule doesn't work when the base is too bulky. Here are 3 examples of some giant bulky bases. Imagine that you are using triethylamine, and this lone pair of electrons with all of this steric hindrance around it needs to attack a hydrogen on a carbon. Just because of steric hindrance, it's going to have a much, much easier job to attack a hydrogen on a primary carbon than a tertiary carbon. And that would result in the anti-Zaytsev's product being the major product, meaning major and minor products would be flipped. Our third case when Zaytsev's rule is flipped is when the leaving group is bad at leaving, and that happens when the leaving group is really, really basic. So this has to do with the stability of the transition state. That transition state has some partially negatively charged carbons. Carbons don't like that. And carbocations that are positively charged are stabilized by more alkyl groups, but carbanions that are negatively charged are actually stabilized by fewer alkyl groups. And something that's extremely basic, like fluorine, needs that extra stability in order to actually leave, and that's going to lead to the anti-Zaytsev's product being the major product. So this is a table that shows different leaving groups in reactions that are otherwise exactly the same. It also shows the pKa of their conjugate acid, just because that's something that you can look up relatively easily in a table. You can see a trend here where when the leaving group is more basic, there's less of the Zaytsev's product and more of the anti-Zaytsev's product. But the trend is not actually flipped until we get to fluoride. So if you want to simplify this knowledge to just alkyl fluorides, prefer the anti-Zaytsev's product, you'd be right most of the time. Also, I mentioned fluorine as messing things up back in nucleophilic substitution too. So just remember that when you see fluorine, you need to think twice, whether you're dealing with nucleophilic substitution or elimination. And the fourth common time in which Zaytsev's rule does not work is when there is no anti-paraplanar nor syn-paraplanar beta hydrogen compared to the leaving group. Yeah, so basically, because E2 is a concerted mechanism that happens all in one step, that means we have a bunch of bonds that are all breaking and forming all at the same time. And because of that, our orbitals need to be overlapping in really specific ways for this mechanism to actually occur. And there are 2 and only 2 conformations about this bond that actually work to get E2 to happen, and this is it. So, anti-paraplanar is referring to when this hydrogen on the beta carbon and this leaving group are 180 degrees apart. This is a Newman projection if you are looking along this carbon-carbon bond from this direction. You see hydrogen on the front going up, leaving group on the back going down. This is called anti-paraplanar. A lot of people just abbreviate it to anti, but this is one of the conformations that works. The other is this. This is syn-paraplanar, where the hydrogen and the leaving group are both going the same direction. So if you were looking from here, you see hydrogen and leaving group overlapping. That's a dihedral angle of 0 called syn-paraplanar, sometimes abbreviated as syn. Now, some people refer to this as parallel and anti-parallel, just because that terminology is easy to understand. Other people get really mad when you do that because these are not parallel, they're sticking out to the side. Just do what your teacher wants you to do there. But these are the only 2 conformations that work. The examples I have shown you so far throughout this entire video, this has not mattered. And the reason for that is that the examples I have shown you have all had structures where this carbon-carbon bond has been free to rotate. It doesn't matter because that bond can just rotate until it's in one of these configurations and the reaction happens. This is important though when there is something about the structure of your reactant that limits the free rotation around this bond. So let's talk about an example doing that. So let's say that this is your reactant in an E2 mechanism. Bromine's your leaving group. We have a methyl group here, and I've gone ahead and drawn in the beta hydrogens. So hypothetically, any of these are candidates to react. So if the base were to attack this hydrogen, we would form a double bond here for this product. If a base were to attack one of these two hydrogens, we'd form a double bond here for this product. Let's think about what Zaytsev's rule would say. Zaytsev's rule says that we should count the number of other carbons bonded to these alkene carbons. 1, 2, and here 1, 2, 3. More substituted is the 3. Zaytsev's rule should be this is more stable. But you know what? Not only is it just not the major product, it's not actually formed at all. We need to think carefully about the stereochemistry to figure out why. This would be a good time to get out your molecular model kit and build some cyclohexane derivatives to prove this to yourself, or watch my moldy oldie video where I'm playing with a cyclohexane ring. But I've drawn the chair conformations for this same molecule. Here's one chair conformation, then after a ring flip, here's the other. So we are looking for anti or syn conformation between the leaving group and a hydrogen. Does this fit the bill? This is going straight up, so we would need this is our alpha carbon, these would be our beta carbons. We would need a hydrogen that's either going straight down or straight up. This is not a hydrogen at all. This hydrogen is not in the right conformation. This is neither syn nor anti. This is axial, this is equatorial. It's sticking out to the side at some other angle. So this hydrogen cannot react in this conformation. Looking at this beta carbon, this hydrogen is going straight down. This fits the bill for being anti-periplanar. This is not going straight up. That's an equatorial sticking out at the side. Again, if you have trouble wrapping your head around chair conformations, get out your molecular model kit. This hydrogen could react. That would put our double bond here. And that is not right next to this methyl group. It is the other direction, so that's here. So let's say a chair flip happens and we have our other conformation. This is equatorial. Remember that equatorial groups are not like perfectly equatorial, 90 degrees sticking out at the side. You know, like axial are straight up and down. Equatorial are kind of wonky. This is not going to be a dihedral angle of 0 or 180 to anything. So this conformation isn't going to react at all. So that means the only hydrogen that is going to be able to react is this one. When you are looking at this sort of drawing so that you don't have to get out a molecular model kit or figure out the chair structure every time, what you want to see is that your leaving group and your hydrogen are not both on the same side of the ring. Like you want one coming in and one going out. You don't want them both in the same direction. That is how you would recognize that this hydrogen can react. So this one can't react because they are both in the same direction. This one can't react because bromine and that hydrogen are in the same direction. We have only one product. It is our anti-Zaytsev's product. And it comes about because these particular carbon-carbon bonds are not free to rotate. If you need to be able to recognize the major product when the choice is between cis and trans stereoisomers, also known as E and Z, it builds on what I've just explained here, so that would be a good video to watch next. Thanks for watching Chemistry in a Nutshell. If you feel that I've earned it, please like this video and subscribe to my channel.